So hello everyone, welcome to session 4 of ltspice tutorial. Here in this session we will talk about a brief introduction to dependent sources. So there are 4 dependent sources: voltage dependent voltage source, voltage dependent current source, current dependent voltage source, and current dependent current source. And after that we will talk about AC analysis of the complex circuit. So we will create a complex circuit and we will analyze that circuit using AC analysis. And the next one is importing spice models from internet. When we are doing some projects, we will not have all the models in the ltspice, so we download the spice models from the manufacturer's website and we will learn how to import that to ltspice. So moving on to the session, first let us see about the dependent sources. So these are the E means a voltage dependent voltage source, and after that G is voltage dependent current source, and after that we can see H, which is current dependent voltage source, and F, which is current dependent current source. So let us create a circuit to show this. First we will take a voltage dependent voltage source. We will keep it here. After that we will create a voltage source here, side by side. We use F32, which is the short key for getting wire. We will ground this. After that we have to ground this also. So F3 we can ground. So after that we will press F4 for getting labels, and we will create a label V1. This label we will keep here and here also, so that the voltage at the voltage we get in the V1 here will also come at here. This way we can reduce the usage of wire in our circuit diagram. So let us make a resistor in series with the circuit and see how it works. And we have to ground the resistor. Now we will give a value of 1 volt to the DC source, and here we will make this E as 10. So we are supposed to get a 10 volt output from the dependent source, and we will make this resistor 1K. So I think we can run the circuit and see if this works. So this is the so 1 minute. Okay, so let us run this once more. Yeah, okay, now we can find the output across the resistor, and this is 10 volt as expected, and the voltage at the input also we can see, which is 1 volt. So this is working. So now let us move to the second thing, that is we have to use G. This is the voltage dependent current source. So let us see it's working. So we will keep it here. Now we will ground the positive and negative. We will ground the negative terminal. G is the short key for getting ground, in case you don't remember, and F3 is for wire, connecting wire. Now we press F4 for label and create the label V1 that we done above. So we get a voltage at V1 here also. After that we make a resistor in parallel line series with the dependent source, and we will ground that resistor also. Okay, so that's done. Now we have to give the value here. We can make this also 10, and this resistor value we can make it as 1k. So as we are having a 1 volt as the V1, we are supposed to get an output of 10 ampere through this current source. So let us see, we can run this program and we can find the current through the resistor. Yeah, we are getting 10 ampere as the current as expected. So let us move for the next one, which is H, a current dependent voltage source. H, where is it? Okay, here. Okay. In case of current dependent source, the things are little bit different. So let us see. We use F3 to connect the ground. Okay, we keep the ground. And F3 for wire, and once more we keep a resistor in series. And G for ground. Okay. Now here there is a little bit difference. We can, yeah, for the value of H we should give the current through a voltage source V1, and then the times we are multiplying it. So the voltage source here we are taking is V1. So we give V1, and we need a multiplication factor of 10. So we give 10, V1 space 10. But for that a current should flow through this V1, so that we are connecting a resistor in series with V1 to make a current flow through the V1. Otherwise, the current is not flowing, means it will not work. So we put a ground also here, and F3 for wire. F3 for wire. Okay, so we are giving this value of resistor as 1k. We can give here also, we can make the value of resistor as 1k. So as this is 1k and this is 1 volt, a current of 1 milliampere should flow through this circuit, and 1 milliampere into 10, a voltage of 10 milliampere will be here. That is what we expect. So we can see, we can run the simulation, and the current through here is 1 milliampere as expected. Now we can see the voltage across the dip. Yeah, 10 millivolt or minus 10 millivolt, because the direction is, you can see that. Okay, so this is as expected. Now we can go to the next component, that is a current dependent current source, I guess. Yeah, current dependent current source, which is F, linear current dependent current source. Now we press OK, and now we create a circuit with a resistor in series with the dependent source. Now we connect the grounds, and here also the value of F should be given as a voltage source we should have. So we can take the voltage source capital V1 space 10 times, as usual we take 10 times is the multiplication factor. For this two we have to just give the multiplication factor, and here we should give the current through the voltage source we are taking and then the multiplication factor. Okay, so the current through here is 1 milliampere and we expect 10 milliampere through this. So let us see. Sorry, there was a small mistake. I forgot to give the value for resistor R5. So let me give the value as 1K. Okay, now we can run the program, run the simulation, and the current through this is 10 milliampere as expected. So now, I guess that the dependent voltage sources topic is clear, and now we can move to the second topic, which is AC analysis of a complex circuit. So here we have a complex circuit which is this one. So in this question we have to consider this circuit, and the value of HIE, HFE that I have done in the that will be given later on. So the question is plot the frequency response of the circuit shown below. So to plot the frequency response, we should take AC analysis, because AC analysis gives us the frequency response or the Bode plots. And the second part of the question is estimate the pole locations. Uh, we can estimate that because the pole locations will be 3 dB gain. The gain at the pole location will be 3 dB less than the maximum gain. And we should find the bandwidth, unity gain frequency, and the maximum phase shift. So you can create this circuit as I have shown. I have introduced you to the dependent source concept, so you can uh, make the circuit. I have made that already, so I will explain the circuit. Okay, so this is the circuit. Let me minimize those other tabs. So okay, this is a circuit. We can see that side by side so that the concept will be a little more clear. One minute. Okay, so let me zoom in a little bit. Okay, so we are giving a voltage source here, and we have grounded it, and the ground is not shown in this circuit. For a circuit simulation to work in ltspice, we must give a ground, then only it will work. And this is the first resistor R1, which is of 50 ohms. First capacitor of 1 nanofarad here, and the value of HIE I have taken as 1.5K. That is the value of the resistor only, HIE 1.5K resistor. And here I have kept a voltage source of 0 volt. So do you know why? It is because for this current dependent current source to work, we should have a voltage source. So here we have kept a voltage of 0 as a buffer voltage source. So that in simulation only we do like that, and the actual circuit when we make in laboratory or in the project we don't do like that. It is done in simulation, so that we need a voltage source. We want the current through this branch. You can see clearly in the circuit I1. In the branch I1, the current I1 is multiplied here. So to get the current I1, we keep a voltage source, buffer voltage source of 0 volt here. And in uh, and here we will put V2 comma 165. V2 is this voltage source name. V2 space 165 is the multiplication factor. And R3 is the resistance. Oh, that is 1 by HOE. So that is the resistance value. Here I have taken it as 505,555.55. And C2 is the second capacitor 1 nanofarad, same. And HIE, the value is already taken here, which is 1.5K. Same we take here also, and here also we keep a buffer voltage source as we kept here, because we want this current I2 through this branch. This current we need to be amplified. No, we want that current to be multiplied by a factor. For that we keep a buffer amplifier there. We keep a buffer voltage source of 0 volt there, and the current through that voltage source V3 is multiplied by 165, which is HFE, and the value of R5 5555.55, and C3 is 1 nanofarad. R6 is the resistor 10K, and we have grounded the whole circuit. We have connected the whole circuit and put a common ground here. So the whole circuit is grounded. And for we want to find the voltage here. This voltage output voltage at here. So we can run the circuit, and I assume that you can make the circuit. I have explained everything. So we run the circuit. So we get this plot. So here this plot, right? This is a dotted. We can see it's a dotted line. So that is actually, and this is the phase plot. This is the phase plot, and this is the amplitude plot. So we can find the, so in the question, what are all the questions? We have to find the, we have plotted the frequency response. This is the frequency response. I will show you how I did AC analysis. So here we will give AC analysis. Type of sweep is decade. Number of points for decade is 1000. That you can give, and the starting frequency I gave is 1 millihertz, and the stop frequency is 1 gigahertz. Now I click OK, and we will run it. That is this one, this graph here. Yeah, this graph. So this is the, as I said, this is the amplitude plot, and this is the phase plot. Now in the question we are asked to find the pole locations. So pole locations are the places where the amplitude is 3 dB lesser than the maximum amplitude. So we have to find, here there are two poles. We have to find those two poles. So we click on this VN007, and we find which is the maximum. One minute. We keep the scope here so that we can find the voltage that is asked in the question. The scope is placed here. Now we can look at the graph. Yeah, here we can see. Oh, 1 minute. Let me change this to the side. So here we can see the values. The maximum value that we get is around 93.23 decibel. Here we can see the magnitude. Magnitude we should see 93.23 decibel. Now we have to get 3 dB lower than that. That is 90.23 dB. So 90.23 dB comes around the frequency here is 9 kilohertz. So the first pole frequency is 9 kilohertz. So similarly on the other side we will have a cutoff. So we can find the other cutoff. That will be, that will also be 3 dB less than 90 point something we should get. 90 point near 90.23. That will be the pole frequency. So it is around 90.26, 152 kilohertz. So the pole frequencies are 9 kilohertz and 150 kilohertz. So we have estimated the pole locations. Now next one is bandwidth. Bandwidth is the difference between the pole locations. That is 150 kilohertz minus 9 kilohertz. So the bandwidth is approximately 152 minus 9, which is 143 kilohertz. Approximately 140 kilohertz. 143 kilohertz is the bandwidth. And the unity gain frequency. That is the next thing we have to find. The unity gain frequency is the frequency at which the gain becomes 0 dB. So there will be two unity gain frequencies. So we can find the unity gain frequencies. We have to change it so that the magnitude here becomes 0. And we have to find the point where the magnitude becomes 0. Yeah, it is near 200 millihertz. Around 200 millihertz we are getting one unity gain frequency, and we can find another unity gain frequency, which is, let us find out the other unity gain frequency. Which is around 150 megahertz. One unity gain frequency is at 150 megahertz and the other is at 200 millihertz. So those are the two unity gain frequencies. So we have found the unity gain frequency also. The next thing that we have to find is the maximum phase shift. So I told you that this is the phase plot. So the maximum phase shift is, here the maximum phase shift is 90 degree. You can see that. And it is going up to minus 180 degree. So the maximum phase shift is 90 degree to minus 180 degree. That is the phase shift. So we have analyzed a complex circuit, and now we can move to a third part. Yeah. So we have completed our first two aims, that is in introduction to dependent sources and AC analysis with a complex circuit. And now we can move to importing spice models from internet. So that is a very important part because most of the things that we need, like op amps or transistor models that we use in real life for our projects, may not be available in the LT spice. May not be because there are limited numbers only. For example, op amps, there are so many op amps in LT spice, but there are more than that op amps outside. So we can import for example, an op amp which is LM741 from the Texas Instruments sites. So I will show you. First, we take our browser and we will open a new tab. And now here my aim is to find my aim is to import a LM741 op amp. So we can search for LM741 op amp. Sorry guys, the internet. So okay, our search results are here. So we are going to the this site, which is Texas Instruments site, I guess. ta.com. Yeah, Texas Instruments site. Here we can see. Now we go to design and resources. Oh sorry. We will scroll down and find the pspice model. It will be given design and development. LM741 pspice model. Now we click download here. Now we have to save the download thing. symbol. So I click save, and we are downloading that pspice LM741 pspice model. So whichever op-amp or transistor you need, there will be a model like this in the manufacturer's website. Here the manufacturer is Texas Instruments. So there we should go and click download so as to download the pspice model. Now let me open the downloaded .zip file. This is the .zip file that this is the .zip file there that we just downloaded. So here there is a file .lib file, you can see. .lib file here, lm741.lib. This is the .lib file which we want. This file is required for the model. For that we can take ltspice. Yeah, we can open ltspice side by side, and then first we should extract this. So this is the .lib file. We have to open it in ltspice. We can slide it to ltspice. So what did I just slided this to ltspice, and this came. This is the file .lib file. Here there is dot. Here you can see a text in blue color. So we should just right click on that. Right click on the blue color text, and we will get something called create symbol. Just click on that. Then okay, click on yes. So this is a symbol that we get. But uh, as you can see, I will show you one thing. Yeah, here when we click F2, you can see the symbol for usual op amps. Yeah, this is the usual symbol for op amps. But the symbol that we got with the auto generated symbol that we got is something like this one. But and now we are going to make this symbol into a symbol that we want, like the normal op amp symbol, like this. To do this, you have to follow the steps that I'm going to mention. First you should go to the file. You should go to uh, OSC, then users, my PC, your username. Here there is a little bit problem here. By default, this show hidden files will be often in most of the computers. So there is a folder called app data that you can see in ltspice, I guess. When we click the F2 here, we can see a directory address. See users my PC app data local ltspice here. This is where all the symbols are located. So let us just go there through the directory. So when we come here, we cannot find the app data folder. For that, you should go to view here, and then show hidden items. Then it will show the folder app data. Go to app data, local, ltspice, and here there is a folder called lib. You should go there and sim, and now auto generated folder will be there. This is a symbol for our. So 1 minute. So we should go to the auto. This is the I told you from the lib folder. I am telling once again. ltspice you should go from the to the lib folder, then to the sim. Sim is the short form for symbol, and there is auto generated. Here in ltspice we can see the symbol that you generated now just now, that is in the auto generated folder lm741, this symbol, and we want to transform this to normal op-amp symbol. So we go to auto generated folder here, and here we can see we are going to open with notepad or any other small text editor only. And now we want another normal op-amp. So we go to op-amps, and then we move down to op-amp 2. We can take op-amp 2, I guess. Op-amp 2 symbol is here. So open with notepad. So now we have opened two notepad code files. One is lm741 and the other is op-amp 2. Now here you can see the sim8tr, this part now. From here to this, all this sim8tr part, that is those parts we require, because that this sim8tr part is the part of the uh, properties of the op-amp, and all the other part is the symbol of the op-amp. So we copy the symbol from here, version 4 up to sim8tr. Up to sim8tr we copy, and then we paste here. Okay, and now we delete this. Now after the sim8tr, after this you can see you should copy the below part also, that you should copy to the lm741 up to sim8tr of the lm7 and paste there. Now save the lm741 file, and you can close the notepad files. And now we go back to ltspice, and now we open it once more and auto generated lm741. Oh, why it is like that? Some problem, I guess. Wait, let me see. 1 minute. So now auto generated, open with notepad, open with ltspice. Yeah, the symbol has changed. We can open a new, and now F2, auto generated lm741. The symbol has changed. So this is how we import from this is how we import an op-amp from or any other components. from the internet we import, and then we use the .lib file which is required. And in the op-amp case, I just showed you how to change the symbol. Now if you want, we can just make a small circuit from this op-amp, and non-inverting configuration or inverting configuration we can make. We'll put a ground here, and then a voltage source here. Then we put a resistor F3 for wire. After that, we have to connect one more resistor here. If you know about op amps, you will know this. This is an inverting configuration of an op amp. So we can connect this to the output. So this is the output of the op amp, and here we should give the supply voltage that we can give from outside. Now we join this positive negative and keep a ground here. Here also we keep a ground. And after that, we create labels, because labels is an easy way to use ltspice without using much bias. So we can give the label V plus, and V plus is here, and we keep V plus here also. So the voltage, which is present here will automatically come to here. It is just like connecting by wires, but in simulation this is made easier by these labels. So F4 is the shortcut for accessing labels. F4 and V minus is a new other label. We keep it here, and V minus here also. Now we give the values for this. We can give a DC value of 15 volt. Here also 15 volt, and this resistor we can give a value of 1k, and this resistor a value of 10k, and this voltage source we can give a sine wave, I guess. Sine wave with DC offset 0, and amplitude will be 1 volt. DC offset means the amount by which the center of the sine wave is above the x-axis or the origin, like that. Above the x-axis, that is DC offset. So we want our sine wave symmetrically about the x-axis. So we make the DC offset 0, and the amplitude as 1 volt. We keep the frequency as 1 kilohertz. That's click OK. Now we have to run. Here we are running it in transient analysis. Just give stop time as 1m, and that's enough to click OK. Now it 10k 1k. So if you know about the inverting configuration of op amp, you will know that the gain that we expect is minus R2 by R1, that is minus 10. That is, if we give a sine wave, we should get a sine wave which is 180-degree phase shifted and has a gain of 10. So here the amplitude at the input is 1 volt. So we expect to get an output of 10 volt amplitude and 180-degree phase shifted. So let us see if it works. Run. We can see the output wave and the input wave also we can see. Yeah, it is working. So for the input wave alone, it is a 1 volt peak to peak. No, 1 volt maximum amplitude. That is 2 volt peak to peak sine wave, which is starting at 0 volt because it is 0. Or we gave the offset as 0, so it is starting at 0 volt. Maximum it goes to 1 volt, minimum to minus 1 volt. And let me turn on the grid here. View grid of, yeah, you can see that the sine wave is symmetrical with the x-axis, and here the sine wave first goes up then goes down. Now we can look at the output wave. Now here we can see that it is minus 10. The maximum amplitude we get is 10 volt, but as the 1 volt amplitude sine wave goes up, this sine wave goes down. That is the 180-degree phase shift, because you know it, I guess. 180-degree phase shift happens minus R2 by R1. If you don't know, you will study it when you learn about op amps. It's the inverting configuration of an op amp. If you are too curious, you can just search the web for it. So we get as expected. So that's all. I guess we have covered everything. Session 4, we have had a brief introduction of dependent sources. We analyzed an AC complex circuit, which is this circuit we analyzed, which had capacitors. And one more thing here, the cause for this nodes, for the cause for this poles is the capacitors. Because of this capacitors only the poles are coming. So we have done the brief introduction of dependent sources, AC analysis with complex circuit, and we have also learned how to import spice models from internet and how to change their shape. So the more important thing is that you should not change the sim ATR part, this part, right? This should not be changed. The this part means the this part shows how the particular thing like op amp, how it should behave. That is this part showing, and the other part is how the about the symbol of the op amp. So that's all in this session. Thank you guys.